The way we set it up is uh, this class and the next class is about chapter 17. So we actually get an extra class. So I'm going to finish up where I left last time. I couldn't finish the last problem. So I'll do this and I'll get to 17.5, which is on general planar motion. Okay. So so this is a problem on rotation about fixed axis, just continuation of last class. The cable is unwound from a spool supported on small rollers at A and B by exerting a force T, and that's a constant, 300 newtons. Compute the time needed. So the unknown is the time to unravel 5 meters. So let's call the distance unraveled as delta S, that's 5 meters. From the spool, if the spool and cable have a total mass of 600 kilogram and radius of gyration of 1.2. For the calculation, neglect the mass of the cable being unwound and the mass of the rollers at A and B. The rollers turn with no friction. Okay. Okay, so what's happening here is that force T equals 300 newtons is constant. Because of that force, this cylinder is rotating about this axis supported by the rollers. You're going to find the time it requires for 5 meters of cable length. The time it takes for 5 meters of the cable length to be unwound from that particular spool. Okay, so the spool spins about O, even though it's supported rollers, it spins about O. So it's a problem on rotation about a fixed axis. Okay, we are asked to find the time it takes to unravel 5 meters, but this is really a problem on rotation. So what we'll try to do is we'll try to relate the displacement of the cable 5 meters with an angular rotation, right? So if 5 meters in on moon, what is the angle turned by the spool? So once we find that theta, or once it's turned, we can then try to relate that with acceleration in order to solve for the time. So we're trying to get to the acceleration, which will then integrate to solve for theta, which in turn will be related to s. So that's how I will proceed. So since I need to find the acceleration and there's a force involved, this is a kinetics problem. I'm going to draw the free body diagram first for the cylinder. Now, what's true for cylinders is that when there's a reaction force, okay, it's always normal to the surface. So in this case, the reaction force passes through the center of the rollers and also passes through the center of the other rollers, because the normal passes through the center of either circle. So this is the normal force at A. Similarly, this is the normal force at B. Now we're going to assume there's gravity. So the gravity force is mg. And somewhere here, right, there is the tension force. Okay, so something I want to mention is when you're doing rigid body kinetics, it's very important to put the force in the right place. So one common mistake people do is they take this force and put it over here. Okay. Well, that is not right for a rigid body, because this force has a moment about, it creates a certain moment. So if you put it over here, it will create a different moment. So it's very important to place the force in the right place. It's a very common mistake. You put the force in the wrong place, and you see that that moment creates a moment. Don't do that. Put the force in the right place. So it's important to draw big pictures. So people with very tiny pictures for this rigid bodies, they end up putting forces anywhere. So draw big pictures. For particles, it doesn't really matter where you put the force. By that I mean it's okay to put it. So if this was a particle, then you can put the force here. That's not a problem, because we're never going to use the moment equation. But for this problem, we will use the moment equation. Okay, so again, what I'm after is the angular acceleration. And if you want to solve for angular acceleration, you're not interested in the reaction forces. So I will not try to write F equals ma, because F equals ma will help me solve for NA and NB. What I'll do instead is take moments about point O. Since all the forces act at O, that is the unknowns, NA and NB, the effect of the moment due to those forces is going to be 0, and I'll be able to solve for alpha or angular acceleration in a single equation. So take moments about point O is equals IO times alpha. The moment due to NA and NB is clearly 0, and mg of course is 0. The only moment we get is due to the tension T, and that should be at a distance of, I think it's 0.8 meters. So T times 0.8. So is it positive or negative? It's negative, because about O, if you apply force P, it's going to create a clockwise torque. Now for a disk, the inertia is actually mr squared divided by 2. However, if you're given the radius of gyration, which in this case you have been given, you should just use that. So if you're given the radius of gyration, then the inertia is the mass times the radius of gyration squared times alpha, which is the unknown. So the tension is 300 times 0.8 equals the mass, which is 600 kilograms, times the radius of gyration square. So this will help me solve for alpha. Alpha is minus 0.2778 radians per second square. The negative sign indicates that the spool is spinning clockwise direction, right? Our convention is counterclockwise, alpha is positive this way, but the spool is spinning this way, so it's clockwise. So the last part is kinematics. We're given delta S is 5 meters. Okay, delta S is the radius times delta theta, right? What is R? R is 0.8, which is this, times delta theta. Okay. What I'm trying to do here is I'm trying to see how much the spool has rotated when 5 meters of length has been unwound from the spool. So 5 equals 0.8 times delta theta. This gives me delta theta is 6.25 radians. That means that the spool is rotated at about 6.25 radians. It's about 2 rotations, right? One rotation is about 3.14, so it's about 2 rotations. Okay, now I'll try to relate. So since I'm interested in finding the time it takes to unwound that much cable, I'll try to relate delta theta with alpha through time. Now the good news is that alpha is a constant. If alpha is a constant, then you can use the formulas which we derived long time back. The constant constant acceleration formula. So one of the formula is, so there are three, right? Omega equals omega 0 plus alpha t, s equals alpha equals theta 0 plus omega 0 t plus alpha t square. And the third one is omega square equals omega 0 square plus 2 alpha theta. So in this case, I'm only going to write this formula just because I know alpha, I know theta, I do not know time. Okay. Okay, this thing is delta theta, which is 6.25. So 6.25 equals, what's the initial speed? Is it 0? Okay. Does it say anything it's 0? No, it doesn't say anything, but I'm going to assume that it's, so assume the initial speed is 0. So 0 plus half times 0.2778 times t squared. Well, this is really negative, and to be really particular, I need to put negative because it's negative, right? That's what I got. But I need to put negative 6.25 because the rotation, the angle turned is clockwise and not counterclockwise. So counterclockwise is positive, clockwise is negative. So I need to put that CW. So I can solve for t from this. Comes out to be 6.71 second. Okay, any questions on this?
Yeah, when you draw MG, if you draw it from the center of it, then that would be wrong. Like it's going to the center of the object.
It is going through the center of the object, right?
Like the arrowhead, if you draw. Like,
Oh, if you draw it this way?
Yeah.
That's fine. That's fine. Yeah. Okay, any other questions? Okay, so let's move on to 17.5, and really we have, I believe, 1.5 lecture to cover this, and this is probably it's very important. In the past, we have given questions on this particular section. So 17.5 is the last section in 17, chapter 17, and this is kind of important because this is general planar motion. So motion involving translation as well as rotation, right? Previously, two lectures back, we did only translation, and then the last section was only rotation. But this is going to combine the two, translation and rotation. So we'll be talking about rolling and sliding wheels. We'll also look at static and kinetic friction, and the key thing is general planar motion. Okay, what we've done so far are special cases of general planar motion. Okay, so let's write a few formulas before we start solving problems. Okay, so general caricature of a body which is subjected to moments and forces. We can write, so this is going to be my F, B, D. And some of those forces which I've drawn may include reaction forces. They may be unknowns. Okay, Fx is mass times acceleration in the x direction. Fy is mass times acceleration in the y direction, and mg is ig alpha. So you see that the formula here, which I've written down, is identical to the formula which I wrote down for a fixed rotation case. Okay, it's identical. But what you see is that sometimes it's not ideal to take moments about g. When it's not ideal to take moments about g is, well, let's say f3 was an unknown. If f3 was an unknown, it'll actually show up in this equation, because when you take moments about g, then f3 would have a moment out. So you might be interested in taking moments about a different point. It could be some point here, there. So we need to be able to write that equation too. So that will make your life easy, as you'll see when you solve problems. So another way of writing the equations is take moments about a different point. So I'm going to give the complete set of equations. The force equilibrium equations hold true. However, we are interested in take moments about some other point P. Okay, let's call this point as P, and we will take moments about point P. If we take moments about point P, the equation is, and this is probably the most important formula in this section. I'm sort of abusing notation here. I have in that equation I did not write it as a vector. Here I wrote it as a vector just because this terms are vectors, but this equation is a single equation because it's all moments about a particular point for a planar motion, so it's all about k. Okay, so ig alpha stays as it is. However, you get this term. Okay, what's this term? Well, this is the moment arm due to acceleration about point P. So you got to find the vector from P to G. This is a vector from P to G. This way. Right? Once you find the momentum, you need to multiply it with mass times acceleration of G. So this is the second set of equations. Okay, the only difference is the third equation that changes. Okay, so here is the technique. This is essentially the repeat of what we did in chapter 13 or previously, right? Once you identify it's a kinetics problem, you draw the free body diagram, write equations of motion. Okay, this could be moment about P2, Ig alpha. It really depends on the question. And then finally, and this is optional, you do the kinematics to solve for position of velocity. Okay, so we'll apply this with a few problems.